This program is brought to you by Stanford University.
So today I'm going to discuss different options for addressing climate and air pollution and look at the impacts on other externalities as well of these different energy solutions. So I'll explain that in a second, but I just want to start by motivating it a little bit with looking at why are we interested in these renewable and other energy solutions to climate change and air pollution. Well, with respect to global warming, we're all familiar with that temperatures are rising, but I want to point out that the temperature rise so far, which is about 0.8 to 0.85 degrees Celsius, is due to a combination of greenhouse gases plus fossil fuel soot, and some biofuel soot, which is the second most important component of global warming after carbon dioxide. Carbon dioxide makes up about 0.9 of the, this is the net observed warming of 0.8 to 0.85 degrees, but there's greenhouse gas warming of 1.6 degrees, and of that, about 0.9 degrees is due to CO2, and fossil fuel soot is about 0.3 degrees Celsius, the second most important component, and then methane is next. And then there's a little bit of urban heat island, but there's offsetting all this warming is some cooling going on by air pollution particles that as you clean up air pollution, you're going to unmask. This is going to go down fast, and this will go down, but the warming should accelerate. So it's very critical to, even if you don't emit a lot more CO2, the temperatures could go up significantly as we clean up air pollution. And this makes it extra critically important to address climate by, in fact, you need an 80% reduction in CO2 and other warming component emissions pretty much immediately to stabilize temperatures. So 80% reduction is necessary. So any technology that doesn't reduce emissions by 80% is really going to be detrimental compared with those technologies that do. So I'm going to compare the following, I'm going to put everything on an equal footing by looking at vehicle technologies, but I'm going to look at different electricity sources for vehicle technologies. The vehicles will be battery electric vehicles, hydrogen fuel cell vehicles, and then flex fuel vehicles. And in the case of battery electrics, I'll look at different electricity sources, including wind, photovoltaics, concentrated solar, geothermal, tidal wave, hydroelectric, nuclear, and coal with carbon capture and sequestration. For hydrogen, I'm going to look at wind, and all these other ones will be analogous. You could pretty much scale the results, but it's going to focus on the wind-producing hydrogen. And then I'm going to look at cellulosic and corn ethanol producing energy for flex fuel vehicles. And I'm going to compare these all with respect to resource abundance, carbon dioxide equivalent emissions. And when I look at this, so this is life cycle, I'm going to look at the normal life cycle emissions of these different energy technologies, but then opportunity cost emissions, leakage from carbon capture and storage, and then nuclear war terrorism emissions risk from nuclear energy expansion. And then I'm going to look at air pollution mortality effects, water consumption, footprint on the ground of each technology, the spacing required, effects on wildlife, thermal pollution, water pollution, and energy supply disruption and normal operating reliability. So I'm going to do that all in the next half hour. So you will get a result. Okay, so let's start with resource availability, and we'll just look at a few of these electricity sources first. So look at wind. So we did this mapping study, which I'll show you some results for in a second. But based on this is just from data. If we look at from data alone, from soundings worldwide and surface stations combined, we found that there are about 72 terawatts of deliverable electricity, not the installed power, the deliverable electricity from wind over land at locations where the wind speed is 6.9 meters per second or faster, which is the wind speed you want in the annual average for the cost of wind to be relatively competitive. And this represents about 15%, well, 13 to 15% of the land area has these wind speeds outside of Antarctica. And so as a result, you're already excluding 85% of the land area. So and then we take another 30% exclusion in that, from that total area, and we come up with a potential of around 47 terawatts, even though there's certainly room depending on what else can be excluded. And this is the current wind delivered power worldwide. It's only 0.02 terawatts. Now, this shows the global electric power demand as 1.6 to 1.8 terawatts and the global overall power demand of 9.4 to 13.6. Of course, if you go to electric vehicles, which are about 4 to 5 times more efficient than fossil fuel vehicles, this total would go down. But even with this total, you can see that there's plenty of wind to power the entire world several times over, all power right now. But there's even more solar, although it's right now more expensive. So solar, if you captured, you put solar panels pretty much everywhere, except enough space to walk around them on land, you have about 1,700 terawatts of solar available, with a potential, if you take away high latitudes and some other places, of 340 terawatts, and there's even less installed. Now, geothermal, of course, it depends on how deep you go. You can go to the center of the earth, of course, and get really lots of energy. But the geothermal industry estimates about 0.15 terawatts, although this may change as technologies get better. But there's still, there's more geothermal currently installed than solar. Hydroelectric, this is currently the most abundant of all these technologies currently installed, but there's not a whole lot of room for further growth of hydro. But we'll see the existing hydro is going to serve an important purpose. And then wave plus tidal, there's some here as well, and this will be potentially important. But I want to point out that either wind or solar, they can satisfy the entire world energy demand if you actually focus on them. But you really want a combination of all these electricity options, as we'll see. So let's just look briefly at the world, or the North America wind resource that we obtained. This was from the first atlas of the world's winds based on data at 80 meters, the height of modern turbines. And well, it's well known that there are strong winds in the Great Plains, but we found there are strong winds here offshore, as anybody from Galveston knows. But there's also strong winds along the East Coast, but the nice thing about the East Coast is there's a lot of shallow water. And our group, including Mike Dvorak, who's here, I think, has been looking at the West Coast and has found some strong winds there, although the water is deeper, faster off the West Coast. But there are a lot of places, and this only shows each dot represents a pinpoint location. But it turns out that it's about 15% to 17% of the US has fast enough winds for the wind electricity price from that wind to be cost competitive. Of course, the transmission is a limiting issue. But 15% is really an important number because you only need 0.5% of that area to power the entire US vehicle fleet, or 0.5% of the US, with wind turbine spacing, to account for the wind turbine spacing. And it'll turn out to be about only 1 to 2 square kilometers of actual footprint on the ground, which will be an important issue. So let's start by looking at the CO2 equivalent emissions. I want to talk about what are the overall CO2 emissions, and they're going to be the sum of several factors. So one is the normal life cycle CO2 emissions, and let's start with the electricity sector. Of these, coal, with carbon capture and sequestration, this is when you have a carbon capture, it's estimated that you'll take out 90% of the exhaust of CO2. So you still have 10% of the exhaust, but you still have a lot of emissions from the mining and transport of coal. And leakage is not included in here. I'll show that in a later figure. But there's also the cost of the power plant, the CO2 emissions from developing the power plant, but mostly the mining, the transport of the coal causes this. And each of these bars has a low number and a high number. So these are low estimate and high estimate based on data. And so there's still a lot of emissions, even with carbon capture and sequestration with coal CCS. Now with nuclear, it's not carbon free, even if you just look at the life cycle and ignore everything else, which you can't do. Now, the nuclear industry estimates this number for the CO2 emissions. So I said, okay, let's put this as the low number. This is the life cycle emissions from the nuclear industry. This high number is actually not even the high number. This is the average of 133 scientific studies. And so but you assume in the future, there'll be improvements, so I use the average as the high number. So the nuclear CO2 emissions from life cycle alone are actually relatively they're not as low as some of these other ones. Solar PV has relatively high CO2 emissions if you look at the life cycle, but it's also getting better, and it's getting better than it was, and you'll see some of the other benefits of it later. And geothermal, there's a range, again, depending on different studies. But these other ones, CSP and wind, have the lowest of the life cycle emissions estimates from the literature. If you look at, but they depend, like for example, wind, it depends significantly on the wind speed. If you put your turbine in a low wind speed location, then you're not going to get a good life cycle. But if you put it in only the locations that are 6.9 meters per second or faster, which you would want to do if you want it to be cost competitive and you don't need it to put it in other places, then this is what you get, a very low life cycle emissions for CO2. So then there's another emissions associated with each of these technologies. That's the opportunity cost due to the delay between planning and operation. So if you want to put up a nuclear power plant, then it's going to, you don't start getting the benefit of the life cycle emissions until the plant is actually operating. But in the meantime, you're emitting stuff from the regular electricity grid, which is mostly coal currently. So it takes anywhere from 10 to 19 years to actually put up and to get a nuclear power plant operating. And 10 years is very optimistic, and this is with new regulations in the United States. But the construction time is 4 to 9 years, and the 4 years is what the low value from Europe and Japan today. But in addition to this construction time, there's a permitting time and a construction permit approval and issue time. And so you get a total of 10 to 19 years. So during that time, if you decide you want to put up nuclear power plants, you're going to be emitting from the regular grid. Whereas some of these other technologies, most of these, only take 2 to 5 years. So you take the difference between this time, and you're going to get emissions for these other technologies that take longer for that period of time that have to be accounted in the life cycle. So for hydroelectric, there's also a long time, 8 to 16 years. But the hydroelectric plant can last 80 years or even longer. So after, for example, 40 years of a nuclear power plant, you have to refurbish it, and that's going to take another 2 years of downtime. And so there's going to be additional emissions at that point. But for hydro, even though there's a long startup time, you won't have to refurbish it until 80 years or even longer. And coal with carbon capture, it takes 6 to 11 years, so there's also an opportunity cost. So anyway, you get the picture. And so if you actually graph this, these are additional emissions you need to add on to those other life cycle emissions to get a better estimate of the life cycle. So then the next thing is with nuclear energy. Okay, so there's nuclear energy proliferation is associated one-to-one with nuclear weapons proliferation. And this is not trying to be controversial, it's just a fact. I mean, there is no technical demarcation between the military and civilian use of nuclear reactors. And to date, there are 42 countries today that have fissionable material that can be used to produce nuclear weapons. 9 have nuclear stockpiles. 22 countries have fissionable material, have facilities in nuclear energy plants to produce enriched uranium or to separate plutonium. 13 of 42 countries are active in producing enriched uranium or separating plutonium. It is only with the presence of nuclear energy facilities, nuclear power plants, that countries of the world will produce fissionable material for producing nuclear weapons. And you can see that now with Iran and with Venezuela as they're starting to use their nuclear power plants, or they are using their nuclear power plants, and Venezuela is saying they're going to start with their nuclear power plants, that you're going to get more spread of nuclear weapons. So there's not really an issue, I think, and it's been well known for years. And this is because this Los Alamos report, for example, is from over 15 years ago, that nuclear weapons will be spread with the spread of nuclear energy. So you have to account for the risk of the carbon emissions. And well, there's the death rate that would ensue if you have a nuclear exchange either between two countries or a nuclear terrorism act, the death rate, but also the carbon emissions from the burning of cities. So I'm actually going to quantify that, but then you have to multiply that by the risk of this happening, which on the low end is 0, if there is no exchange, and at the high end is 1, and if there is an exchange. So you have to account for both the low and the high end. Now, in terms of the carbon emissions, if you had a, well, I'll show you the result in a second. So let me come back to the nuclear. But there's one more thing. So I want to show these two things on the same graph. The leakage rate from carbon sequestration. You can calculate the leakage rate as just the injection rate minus the stored mass divided by the time in years. And the stored mass is this equation that relies on the e-folding lifetime of stored material against leakage, which is tau. So the high estimate, both the low and the high estimate are derived from Intergovernmental Panel on Climate Change estimates of the high estimate of tau, which is the time, the leakage e-folding lifetime, 1% leakage over 1,000 years is the high estimate of tau, which is the low leakage rate. And tau is of 5,000 years corresponds to 18% leakage over 1,000 years. Now, natural gas storage has leaked up to 10% over 1,000 years, at least extrapolation is 10% from existing natural gas storage. So this is not unreasonable. So if you account for that in this equation over a 500-year period, which is a reasonable time horizon to look over, then this is the additional CO2 emissions from carbon capture and sequestration, the range. The low number is pretty small, but the high number is much larger. Now, this is the risk of the burning of cities for the carbon emissions. You can calculate how much carbon would be burned if you burned a large megacity from a nuclear exchange. But if you average it over 30 years and then you weight it over the US, scale it back to the US, it's not a huge number. So the huge number will be more in the death rate rather than the carbon emissions. Okay, so you're going to add this plus the opportunity cost plus the normal life cycle cost. And so this is what you get as the total, the equivalent CO2 emissions from electric power sources for each of these technologies. So coal gives you the greatest, followed by nuclear, then there's hydro, but a lot of these are pretty similar. But wind and CSP are by far the best in these scenarios. So then let's look at the biofuels. So start with corn ethanol. Now, there are two studies I want to refer to for the low and the high number. DeLucci from UC Davis has done probably the most detailed study of ethanol, whether it's from cellulose, from cellulosic ethanol, soy biodiesel, and corn ethanol on the life cycle emissions. But he didn't account for a lot of land use change and price impacts, which Searchinger did. And so I'm going to use this as the low number and this is the high number. But what he found was if you use corn ethanol instead of gasoline, you get about a 2.4% reduction in CO2 emissions than gasoline with corn ethanol in the life cycle. But again, this doesn't account for the land use change. But if you go outside the US, it's about 70% increase in China. There's increases in India and Japan and reduction in Chile. And with switchgrass ethanol, it's about 52% less CO2 equivalent emissions than gasoline. But when you add global gridded land use changes, because if you change a field of, of something else to corn, for example, in the United States, that's going to change the price, which will trigger an increase of the land use, chopping down some high carbon intensity land in some other country, and due to price changes and also the change in supply and demand, he found that with corn ethanol on a global scale, there's a net 90%, up to 90% increase in the CO2 equivalent emissions. And with switchgrass ethanol, up to 50% more CO2 equivalent emissions than light-duty gasoline. So these numbers, 52% less to 50% more for cellulosic ethanol, is a big range. But there's certainly uncertainty, but it does suggest that when you don't include land use, you're really not land use change, you're really not getting the right answer. And it turns out that pretty much every estimate of cellulosic ethanol and corn ethanol life cycle emissions except for this study and some other recent studies, has ignored land use change, and so they've suggested that even cellulosic ethanol might be beneficial when in fact it's unlikely to be beneficial in terms of even carbon. So let's put these all on an equal footing and see, well, if we converted all the vehicles today, all the gasoline vehicles today in the US to either battery electric vehicles or battery electrics powered by electricity, or hydrogen fuel cell vehicles, in this case powered by wind, but you could do it, the hydrogen fuel cells powered by something else, or corn and cellulosic ethanol, and then you looked at what's the net CO2 reduction, CO2 equivalent reduction, because about 25% of the CO2 emissions, equivalent emissions in the US total, are from exhaust from vehicles, and another 8% are from upstream emissions. So it's a total of 33%. The best you could reduce if you converted all the vehicles in the US to some zero emitting vehicle or zero carbon emitting vehicle is 33%. So wind comes really close, and so does CSP. And several of these come pretty close. But then, well, we can go to corn ethanol. Chances are we're going to increase it significantly, even in the low end. Cellulosic ethanol, this is the low range and this is the high, but chances are you're going to not going to improve CO2 equivalent emissions either. But the point is, these are all much worse than any of these other options. And coal carbon capture is certainly better than this, but these are better. And same with nuclear. I mean, this is better than even carbon capture, but these other ones in the limit are better than nuclear. So we want to pick the things that are going to give you the best benefit. But this is only one parameter that we're looking at. We want to look at other parameters too. Okay, so let's go to health. So start with ethanol. So I did a study looking at what's the effect of converting all the vehicles in the US from gasoline to ethanol vehicles, regardless of whether the ethanol is produced is cellulosic or corn, and just on the exhaust health effects. And so from that, I had to look at a lot of data on what are the changes in the emissions of different gases and particles when you convert to ethanol. And so from that non-methane organic gases, from all the data I used, there was an increase of 19.6%, but you get a decrease of oxides of nitrogen. And this, for comparison, is some data that came out after this study that really supported the conclusions because, like, for example, the NOx was pretty much the same as I assumed in my study. But the non-methane organics was even higher when you converted to ethanol than I had assumed. So this is a conservative assumption. Then if you look at some of the carcinogens, benzene, butadiene, acetaldehyde, and formaldehyde, I'd assumed that from these other studies about an 80% reduction in benzene, 10% in butadiene, 2,000% increase in acetaldehyde, for a factor of 20, and a 60% increase in formaldehyde. And you can see that this was conservative compared to some more recent data. This I underestimated the reduction, so this was one out of the 6 that could have been lower. But the acetaldehyde was actually, from the new data, is 4,500 times or percent higher, and formaldehyde is higher. So the bottom line is that the overall conclusions I'm going to draw here are conservative based on even more data, and there was another study since then has come out that supported this further. So what should happen? Well, I just want to point out, so you're getting, with ethanol, you're getting an increase in non-methane organic gases, and a decrease of oxides of nitrogen. So how should that affect air pollution, like ozone in particular, in a place like Los Angeles, which already has significant health problems? People have significant health problems. So we can get that from what's called an ozone isopleth. Here's organic gases down here and oxides of nitrogen. And these are contours of ozone. So if I put this simply, if Los Angeles is up here on this isopleth, in other words, there's a high ratio of oxides of nitrogen to organics. And this is, these contours are increasing levels of ozone. So if I just increase the organic gases without changing anything else, you go to a higher contour of ozone, so you increase the ozone. If I decrease the oxides of nitrogen up here, it turns out you also increase the ozone because you go to a slightly higher contour. So ethanol does both. It increases the organic gases and it decreases the NOx. So you go this way and you go to a higher ozone. So without even doing any calculations, you can guess that if you convert to ethanol fuel vehicles in Los Angeles, you should increase the ozone. So, but I did do calculations in 3 dimensions accounting for many physical and chemical processes. So here's the population distribution of Los Angeles, and here's the change in ozone that would occur in 2020 if you get a 60% reduction in both due to improved vehicles, from both ethanol vehicles and gasoline vehicles. You still get this increase in ozone that's significant, but you can guess that from the ozone isopleth. So this translates into about a 9% increase in the death rate in Los Angeles by converting to ethanol, regardless if it's corn or cellulosic. With cancers, it didn't change very much. On the US as a whole, there's about a 4% increase in the ozone from this study. But that's not it. So then let's look at the upstream emissions of cellulosic, corn, and ethanol, and then gasoline. So DeLucci's study looked at the change in emissions from the upstream, which is in the refining and production of these ethanols, which you don't hear about. You don't hear about the upstream emissions of anything except CO2, because people focus only on the CO2 equivalent emissions, but not the air pollution emissions. But this is really interesting. This is, by the way, is on a logarithmic scale. So the red is gasoline. And focus on this, because this is a particle black carbon, which is the most important component of the health of all of these, because particles cause the most health damage. So you're getting about a factor of 6 increase in your particulate matter when you go to either corn or cellulosic ethanol compared to gasoline from the upstream, not the exhaust. This is just the upstream. But cellulosic ethanol is, well, it's probably within the margin of error, but it's slightly worse than the corn ethanol in this case. So if we combine these together, here's the death rate due to gasoline. Right now, there are about 100,000 people die per year in the US, 50 to 100,000, sorry, prematurely due to air pollution. And right now, it's about 20,000 or so, 20 to 25,000 due to vehicles. But in 2020, because of improvements, it might be around 15,000. But when you go to ethanol, corn ethanol, you'll add this, the red part here, the small amount is that additional combustion health effect death rate. And the black is the additional upstream death rate due to that last graph I just showed you. So you're not getting any real improvement over gasoline, you're getting something slightly worse, and it could be that cellulosic might be even slightly worse than the corn ethanol. Now, if we go to nuclear, since it's sticking out here like a sore thumb, well, if you ignore this brown part, this is the death rate associated with just the normal life cycle emissions, because you have to, from the coal that's burned and the transport and the mining of the uranium, et cetera, to run the nuclear power plant. And this brown is the upper limit if there is a nuclear exchange, that the same as that resulted in that small carbon change. So in the upper limit, this would actually produce more deaths on average over 30 years. This is averaged over 30 years, just for one exchange, by the way, than the annual death rates of cellulose. But this on average, the average of these death rates is greater than this, but in the limit, this is higher. Now, with carbon capture, you also get deaths due to the air pollution emissions. But these other ones, you can see, they're really low in comparison. So again, we want to look at what's the best. If you're trying to pick technologies that are solving air pollution, health problems, and climate problems, you want to pick the best. There's no point in picking your second or third string quarterback or your beta DVD player. Okay. So now let's go to spacing, land's use and spacing. So start with the number of plants needed to run all US vehicles on battery electric. Well, if you want to do that, you would need about 202 to 275 850 megawatt nuclear power plants. And you currently have about 104 nuclear power plants in the US for all purposes. So you'd have to double, increase the total by another factor of 2. Or you need 270 to 365 1,300 megawatt hydroelectrics, 460 to 1,000 coal carbon capture plants, 1,500 to 2,250 geothermal plants, 5,900 to 15,400 solar concentrated solar power plants, 4.6 to 12.5 billion 160 watt panels on your roof, or 770,000 to 1.275 million, 0.75 megawatt wave devices, or 400,000 to a million 1 megawatt tidal turbines, or 73,000 to 144,000 5 megawatt wind turbines. So, I mean, actually some of these numbers are not bad, but I want to focus a little bit on how much space all this takes. So each wind turbine is, for example, a tube that touches the ground, and then it goes up, and then there's things spinning around. So there's two types of spacing that's important. There's the footprint on the ground, and there's a spacing between. So several of these technologies require spacing. The wind, the tidal, because tidal turbines are like wind turbines just under the water. The nuclear power plants, because there's a buffer zone around the nuclear plants as well. And CSP, there's some spacing, but it's, wave power, there's spacing. Now, CSP is not too much spacing. But let's look first at the spacing. Well, first, to run all the vehicles on wind, if you just multiply the diameter of each tubular tower with some little space around it for concrete or construction, and you multiply that through by about 100,000 turbines, what you find is the total land area required to run the entire vehicle fleet in the US is 1 to 2 square kilometers. To run the entire vehicle fleet, you just need 1 to 2 square kilometers of actual land. But you need spacing, which can be used for other things. So that's going to be the baseline. And now let's look at compare the other technologies. So if we normalize the wind area to 1, now we can look at the relative footprint on the ground of these other technologies. Well, wind for battery electric vehicles. For hydrogen fuel cell vehicles, you need about 3 times more wind turbines than for battery electrics, because hydrogen is about 3 times less efficient than battery electrics, but it still turns out to be pretty good. CSP, you'll need about almost 10,000 times more space. Photovoltaics, it's a little, maybe closer to 5,000. Geothermal for battery electrics, it's on the order of less than 1,000 times. Tidal, wave are also less than 1,000 times the footprint. Hydro is maybe 100,000 times. But nuclear is on the order of 1,000 times greater footprint. In carbon capture, similar. Corn ethanol and cellulosic ethanol are about 100,000 times more space, land area. Here's the state of California, and here's Rhode Island. But I'll show you a map in a second. But first, let's look at the spacing, because that was the footprint. So I told you before that to do this with wind, you need about 0.5% of the US. And so here's the spacing required for wind for battery electric vehicles. For hydrogen fuel cell vehicles, about 3 times more. But you'll need less overall space for CSP. And I'll show you a map for the solar versus the wind in a second. And for PVs, it's low. Geothermal, tidal, wave, and nuclear and carbon capture, it's low in terms of the spacing, but not the footprint. Hydro still requires a lot of real space, and corn ethanol and cellulosic ethanol. And the cellulosic ethanol is actually higher than corn ethanol because it actually, from the most recent studies, takes more land to produce cellulosic ethanol than it does for corn ethanol. So let's look at a map of the actual US that would be needed to run all the vehicles in the US. So here's for this yellow is the spacing required for corn ethanol. So it's 9.8 to 17.6 of the entire US, including Alaska. Cellulosic ethanol is between the low is 4.7 and the high is 35.4%. So these are averages of these numbers, these diagrams. For wind, this is the spacing, this green area, and the footprint is this dot, which is actually much smaller than this. And for solar PVs, it's 0.077 to 0.18%. So that would be the lowest in terms of the spacing. But in terms of the footprint, that's going to be important because remember, the footprint's what controls the change in the land use. So if you're covering up land, I mean, wildlife can't live there anymore, and you're pretty much can't use that land for anything else. Whereas if you're just putting a tube in the ground, you can use that land either for cattle grazing, you can use it for farming and other purposes, or leave it as empty space. So then let's look at the water consumption by these different technologies. So these thermal technologies, well, nuclear and carbon capture require water for cooling. CSP requires water for cooling as well, and also washing the devices. But corn and ethanol in particular requires a lot of water because for irrigation. Only 12% or 13% of the corn is irrigated, but that accounts for most of all this water required. So even if you don't irrigate 88% of your corn for corn ethanol, you still require all this water. Cellulosic ethanol, it's not going to be irrigated nearly so much as corn, but it'll still be irrigated to some degrees if you want to get higher productivity. So there's water requirements, but again, these other technologies really don't require any water. And then, okay, so let's look at reliability and intermittency. So people say, well, problem with several of these energy sources is that they are intermittent, like solar, there's cloud cover, there's nighttime. With wind, the wind may not be blowing at some times. But it turns out that take wind for example, if you geographically interconnect wind, you can smooth out the supply significantly. So I'll come back to this, and that's shown here, where this shows 80% of Spain's wind farms interconnected together on the utility grid, and shows that you get this is hour by hour, or even minute by minute, but shown on hours, shows that you get relatively smooth supply. It's not like the wind supply is just really jagged. When you interconnect geographically dispersed wind, what happens is you smooth out the supply, because fast winds at one place are compensated by slow winds somewhere else, and vice versa. So the greater the number of wind turbines over a larger area, the smoother your supply. So one way to reduce that intermittency problem is just to interconnect geographically dispersed wind farms. But another is just to combine wind with solar and geothermal and other power sources. So here shows 2020, with the current demand kind of increased according to the California Energy Commission to 2020 estimates. This is for a July day. This is hour of the day. And we use hydro. Well, the baseline, this is converting 80% of the electricity in California to some renewable, either geothermal, wind, solar, or hydro, where the hydro is not changed from today. There's no increase in the hydro. It's just used differently than today. But it shows that if you have solar, solar will balance some of the wind. So the overall is the demand. Wind in California, a lot of places peaks at night, which would be good for charging vehicles, of course. But solar complements that by filling in a lot of the day. And then this is geothermal, this green. It's just because it's usually used as base load. And you can fill in the blanks with hydro. And this can be done if you do this on a large enough scale and you use you interconnect your resources well. Of course, it requires good transmission and improved transmission, because that's the limiting factor right now, is transmission. Okay, so if we go to, I'm going to summarize now, and there's a lot more information in this paper that I'll refer to later, and how this came about. But you look at all these different factors, and then you weight them according to their importance, and you do a summation, and you do a ranking, and you can find from that, in terms of all these externalities, what are the best technologies with ignoring price or cost. Because policy decisions should not be based on cost. In fact, they aren't under the Clean Air Act amendments. Under the Clean Air Act amendments, cost is prohibitive to be used as a metric for determining what technologies or what rules should be implemented. And that's why you want to set policy decisions, because policies are geared to reduce the cost. So why would you use cost as part of the rationale for deciding whether you should reduce costs? But anyway, so wind for battery electric vehicles turns out to be by far the most efficient at addressing climate, air pollution, health problems, as well as water supply and these other variables. Hydrogen fuel cell vehicles, even though they're less efficient, came up second in this. CSP is close. I mean, these are all good solutions. Hydro has some problems with it, but without increasing it, it's really good, though, for this load balancing. That's why it's still a good source. If you look at the CO2 equivalent emissions, they're pretty low, and the air pollution death rates are low for hydro. It just has other problems with regard to water and land use, and also other environmental effects that are significant. But it does have the benefit of being able to balance, because you can turn it on and off within 15 or 20 seconds when it's in spinning reserve mode. So when you have these other intermittent resources, it can be used to balance them. So hydro is included as something that would be recommended, although you wouldn't expand it very much. But all these others are just much more superior than the carbon capture and storage, the nuclear option, corn ethanol, or cellulosic ethanol, which came out last in this talk. So I'm going to stop there because I do have some other slides, but I don't want to open it up to any questions you might have on that. Yes.
Okay, if you were doing life cycle costs, would they win, also win?
Well, I did do life cycle costs.
But you were doing everything but costs.
Oh, well, sorry. When you say life cycle costs, I thought you meant life cycle CO2 costs. Oh, would wind win? I don't know. I mean, wind is 3 to 5 cents a kilowatt hour over land. Over water, it's more expensive. If you do it on a large scale, if you put it in the right location, it would be competitive. Yeah, it would be competitive. I mean, the cost of natural gas is with ignoring the price fluctuation of natural gas from the DOE, it's like 3 to 4 cents a kilowatt hour. New coal, 3 to 4 cents a kilowatt hour. Wind, 3 to 5 cents a kilowatt hour, depending on where you put it. I think you had the first one.
How do you factor in the conversion efficiency that you're comparing? If you're talking about vehicles, you're talking about gasoline usage in current vehicles, and using ethanol and corn cellulosic ethanol, you get less efficiency in terms of miles per gallon. And then, of course, if you're talking about electric, you've got a different kind of conversion. How do you factor that in?
It's all factored in. So the best way to, here's my conclusions. Well, you can read this. Actually, at this website, there's an article that has a spreadsheet. It shows you exactly how it's converted. It is accounted for. But basically, for like battery electric vehicles, the efficiency is between, from the electricity you put in to the actual motive force, it's about between 75% and 86% efficient. Whereas a gasoline internal combustion, on average, over the U.S., including trucks and small cars, is about 17% efficient today. And then you go to hydrogen fuel cells. If you account for all the efficiencies in each of the steps, even with wind, it's around 30% efficient. So it's less efficient than batteries, but it's more efficient than the internal combustion. If you take new vehicles, they might get to efficiency close to 30%. But those are, so all the steps that are taken to account for the efficiencies are factored in. Yeah, it is, exactly. I think you had a question. I'll go back. Yeah, go ahead.
In several of these technologies, you will need a large transmission line added to your present system. Does that get factored in here?
That's true. So we do need, there's existing transmission, but it needs to be improved, and that's the main limitation to the future growth. The transmission lines are factored in to the extent, they were considered in terms of the land use required, but the costs weren't considered, so the costs weren't considered. But that's all these technologies require some kind of transmission, or trains. Even if you want to use more coal, you need trains and things like that. So there's that infrastructure with regard to transportation of even the ethanol fuel. You need trucks, because you can't run the ethanol through a pipeline. You have to truck it, train it, or barge it. And that's what causes a lot of these extra emissions that cause the upstream problems. So all of them require some additional infrastructure change. And that's accounted for in terms of the land use and also, but that is the main limitation, but not in terms of cost. Maybe somebody in the back. Yeah.
How is sugarcane ethanol?
Okay, sugarcane ethanol, there wouldn't be a lot in the U.S., okay, but in terms of the life cycle, it's better than corn ethanol in terms of the CO2 equivalent emissions, but it's supposed to be a little worse than cellulosic ethanol. And then when you count for the land use change, all the studies that have done sugarcane have ignored the land use change as well. So when you count for that land use change, you also put it above 100%. I mean, also causes a net damage as well. Particularly, I mean, it depends on what part of South America. A lot of it's grown in South America. You know, what land it's actually replacing. And then and also it's not only the land it's replacing, but sometimes it'll replace other agriculture that then has to move into a rainforest that chops it down, that they chop down the rainforest. So when you account for that land use change, it's going to be somewhere between the cellulosic ethanol and the corn ethanol. Better than corn ethanol, but not as good as cellulosic. Over here.
Yeah, what's your view on compressed natural gas for vehicles and pebble bed nuclear technology?
You say nuclear?
Pebble bed nuclear.
Oh, okay.
That kind of solves the problem about exchange.
Well, firstly, any type of combustion is going to cause air pollution problems. You know, it might be a little better than gasoline, but it's not going to be nearly as good as any of those electricity options. And it doesn't matter what your combustion. The key here is get away from combustion. I mean, hydrogen fuel cell vehicles, you can use natural gas for steam reforming, and that's a chemical process. That's not combustion. And even though that emits CO2, it actually reduces significantly the air pollution emissions. So that's better than combustion of natural gas. So I would say it's, you know, CNG is going to be maybe better than gasoline or equivalent, maybe slightly better, but not as good as even hydrogen production from natural gas. With regard to pebble bed, so that allows you to reprocess the uranium, so you can use the uranium to a greater extent without having to store it. And I didn't even talk about the radioactive waste here, although that is discussed. But that actually makes it easier if somebody wants to, it refines the uranium further, so the uranium that is produced is closer to weapons grade uranium. So there is a risk there, but it is more complicated technology for a terrorist to take advantage of. So there is a trade-off, and plus it's probably not going to be around on a large scale for a while. Here.
How about other uses? This is mainly for transportation, right? But how about for agriculture and buildings and other sources of?
Well, these results for the electricity sources apply to the whole power sector for just electricity as well. You can, so they could lighting in buildings, they would apply as well. So power plus vehicles is the major kind of raw source of energy, but there are. Yeah, I didn't evaluate, you know, for example, efficient changes in efficiencies in buildings, which would be another. There are a lot of things I didn't evaluate here. As you can see, I just try to focus on things that a lot of people are talking about in terms of vehicle technologies or power technologies. Yeah, so maybe here and then in the back.
In the slide right before this one, you were ranking all the different types. You said that hydroelectric wasn't that great because of its water usage, but how much, do you know how much like increase of hydroelectric that was taking into account? Because a lot of hydroelectric sort of already exists.
Yeah. Well, first, it's not so much the water usage. Actually, the water lost by hydro is evaporation from the surface. So it's not actually consumed. And that's proportional. Like, let's say a reservoir has multi-purposes. So some of it's for electric power generation, some is for irrigation, water supply, some is for recreation. So the evaporation that was counted here was really just the fraction of it that's used of the reservoir used for the electric power generation. But you asked if that just accounted for any new power plant, any new hydro would increase or change the CO2, the water use by that amount. Yeah, I mean, the existing hydro does the same thing, but it's there, it's already doing it. So it's not changing anything. And so we can't really increase hydro a whole lot more anyway. There's just not enough hydro around to do that on a large scale. Be over here, then somebody over here. Yeah.
Cost and fairness in the picture, you may disagree about what the right discount rate should be, but people are weighing these things in terms of cost. I'm curious, even if from the perspective of the Clean Air Act, we don't care about cost. We're selecting best available technology. Like, what do you suspect in terms of a portfolio of options what would be the most cost-effective approach?
Well, I mean, it turns out of these approaches, well, geothermal is reasonable. Well, I mean, I'm not an expert on the cost. I don't want to say it, but I mean, I know wind is pretty good in terms of its cost, and photovoltaics, they're more expensive now. CSP can be is lower cost than photovoltaics. So each one of these you could evaluate their cost. But the point I want to make about the cost is if you're thinking about it if you're a policymaker, like in Congress or something, and you want to say, okay, we want to support this technology because it solves the problem at hand, then what you do as a policymaker is you give a subsidy to that. Right now, where are all the subsidies going? Ethanol, nuclear, coal with carbon capture. That's where all the subsidies are going. Even though FutureGen, which was a plant that was going to produce hydrogen, I mean, it put billions of dollars into it and it went under. Okay, it was too expensive, but it was lots of money went into it. So but they made a policy decision to go for that plant and to subsidize it. So this would be looked at from the eyes of a policymaker saying, well, what should we subsidize? Do you want to subsidize something that's not going to have any climate benefit? Because if you added cost to this, then you might conclude that, oh, coal is the cheapest thing to do, let's do that. But then you would ignore the fact that it actually doesn't do anything beneficial, as much as beneficial. So that's the danger you have by mixing in costs here, is that you're going to then end up with a technology, like especially the ethanols, that actually don't do anything and cause negative benefits. So you want to ignore cost when you're deciding which technology to push. But of course, when the actual people implementing are going to be concerned about the cost, I agree with that. Yes, we'll just start over there.
How do you balance, or how would you approach the opportunity costs for deploying wind, which requires, for the wide deployment, a lot of investment in transmission infrastructure, compared to distributed PV, which could get around the transmission infrastructure issue?
Well, it's estimated that with PV, a certain percent, I think it was around 20–30%, would go on roofs, and the rest are in power plants. So you do need transmission for the PVs, except for on the roofs, but the roofs are going to be a portion of the PV spreading. And you'll need transmission for CSP, you'll need transmission for geothermal, you'll need transmission for any of these that are distributed, tidal power, wave power. So you would pursue them simultaneously. There's a 2 to 5 year window. I mean, normally, you look at Cape Wind in Boston, I mean, that's taken longer, but that's a rare case because there's just so much local opposition. But you don't see as much local opposition in most wind developments. So you would pursue the transmission simultaneously. And so hopefully within that period, you'd get the transmission. Maybe somebody else from over here.
What about the life cycle cost, the CO2 emissions for mining the materials that goes into the batteries, and then the disposal of the batteries? Is that factored at all into the analysis?
Yeah, that's legitimate, but that would be, for any type of vehicle, there's a life cycle emissions for the components of the vehicle. And so batteries would replace, say, different engine parts or metals. And so there are life cycle, I have looked at life cycle emission estimates for vehicles, for fossil fuel vehicles currently, and you get X numbers. And when you instead use battery vehicles, you'll have a life cycle emissions that is somewhat equivalent to that. So there's not, I mean, that one's a little less exact or known at this point because a lot of the vehicle technologies aren't fully developed. But you'd have to look at the trade-off between one type of vehicle versus another rather than just say there's an additional life cycle emissions due to batteries. You also have life cycle emissions due to current vehicles and other vehicle types. Maybe, I think you had a question. Yeah.
From what I understand, at least in the U.S., the least efficient energy production is during peak production and peak loads. And so...
Sorry, for which technology? For wind?
In the U.S. in terms of energy production.
Oh, just overall.
Yeah, so for instance in California, when you have peak loads in the summer, during the day, that's when they put online least efficient plants in order to make up that. So in terms of low-hanging fruit, I would think that investing in energy that shaves off those peaks would in fact be your best bet in terms of carbon emission savings right off the top.
Right, well that's where solar is usually does well at those peak times. So certainly pumping up the solar for that purpose is good. But also keep in mind that there's, when we have electric cars, you'll be able to charge them at night, and so that peak load time is going to change too. So those are both beneficial things. I mean, solar is really good for capturing the afternoon peak load, but wind offshore is actually good. I showed you wind mostly over land that's mostly during the night, but offshore it's actually there's a sea breeze that peaks in the afternoon as well. Maybe over here and then over here.
You had mentioned linking with transmission different nodes to reduce the intermittency issue. Are you referring to either just connecting them to the transmission grid as we do now, or are you actually envisioning a linked up independent system of windmills where they all come together at one point and then feed the grid?
No, it would be connecting to the existing grid, but you need to beef up the grid because the transmission lines currently wouldn't take all the capacity. If you want to, they might take the capacity to city A, but not to city B, which is also linked to wind farm C. So you need to increase you can take existing lines or pathways and beef up the lines to make sure there's enough capacity on those lines. But it wouldn't be just just on the wind being together. It would go to the regular grid like it does, but just beefing up that grid. Okay, so you have your...
What policies or other practical actions do you recommend in order to achieve a transition to renewables, in particular wind? And would governmental subsidies be sufficient?
Well, I don't know the numbers, but a lot greater than today. Because remember, we have to increase. Well, let me put this in perspective. If you want 100,000 5-megawatt wind turbines, I mean, in World War II, the U.S. produced 300,000 airplanes over a 7-year period, with most of them in the last 3 years. So wind turbines are larger, but they're less complicated than an airplane, and they take more material. But producing 100,000 is not that significant of a challenge, I think, for this country. But you'd want to do this also on a larger worldwide scale. But there are two types of subsidies that are needed. One is transmission lines, or push for transmission lines, because that's really the limiting factor. I mean, you can produce lots of wind turbines, but unless you have the transmission to connect them, it doesn't help so much. So but a lot of people are working on that. And then for the turbine manufacturers, but it's not so much, for the same energy output. The reason you need a subsidy is coal, when you produce a certain amount of coal, the coal producer gets paid more than the wind producer for the same aggregate energy because the coal is deemed as more reliable. So they might get paid, coal might get paid like 4 cents a kilowatt hour, just making it up, versus like 2.5 cents for wind, even though they're producing the same total electricity. And that's why you need to have a production tax credit. It's not because the cost of wind is much more expensive, it's because they get paid less. And so they need this kind of subsidy. But part of it is because there are no regulations on old coal-fired power plants. They're grandfathered in the Clean Air Act, so they can pollute. So if there are actually tighter regulations to force them to go out of business, make them more expensive to go out of business, then that's why you need the subsidy for these other ones, because there are certain technologies that are polluting, they're not paying for their pollution. So I can't give you a number, but I think some large number. Have it 700 billion.
Okay, just quickly remember the Energy Social, Y2E2, second floor balcony. And next week will be Professor Michael Clare from Hanford College talking. His title is Rising Power, Shrinking Science.